Hello, welcome to my talk. This talk is on the physical modeling technology, Reynolds Similitude. Unlike the physical modeling for marine structures, in which the problems are with free surface of water, Reynolds Similitude might be required for many other model tests of fluid structure interactions, and the most conducted physical model test in wind tunnels. In this talk, the basic requirement will be introduced on what are needed for such physical modeling. Let's first look at the dimensional analysis of a general flow problem. The case we are looking at is the fluid jug of a high-speed flow in a horizontal smooth pipe or in a wind tunnel. Here, the fluid compressibility needs to be included. Thus, the fluid drag can be generally expressed as the function of the pipe diameter, the fluid velocity, the fluid density, fluid viscosity, as well as the speed of the sound. This general expression would be same for the high-speed external flows of an airplane or wings or airfoils. Here we can see the total number of the parameters is 6. Thus n equals 6. Based on the problem, we can determine there are 3 base units: length, mass, and time. Therefore, we have the number m equaling to 3. However, in the dimensional analysis, we have to choose 3 relevant physical parameters for these 3 base units. Obviously, the pipe diameter d can be used for the base unit length. The fluid density used for mass, because mass can be calculated as this. Here, d is already chosen. And the flow velocity for the base unit time, here t can be calculated as in this formula. Again, here d is chosen already. As such, we can calculate the number of the non-dimensional groups or expressions p equaling to n minus m equaling to 3. So this means the problem of 6 physical parameters would become a problem of 3 non-dimensional expressions. Pi1 is the function of the non-dimensional parameter, pi2 and pi3 as this. From the dimensional analysis and the Buckingham pi theorem, we can obtain the relation of the non-dimensional expression simply as this. Here, Cf is the jug coefficient, defined as in this form, and we can take this as the non-dimensional expression pi1, and Re is the Reynolds number, defined as this, termed as pi2, and m is the Mach number, expressed as this, termed as pi3. However, if the problems are for low-speed flows, for instance, the Mach number is less than 0.3, which is about 100 meters per second in the air, the Mach number would have no significant effect on the drag coefficient. Thus, it can be ignored, and then the drag coefficient can be expressed simply as the function as this. It is only dependent on Reynolds number. In the scale physical modeling, the similitude laws play a very important role, and these similitude laws could guarantee the success of the scale physical modeling with 3 similitudes. The first similitude is the geometric similitude, for which the scale model must be geometrically similar to the full-scale structure, meaning in all directions, the length of the structure must be proportional correctly. In some special cases, the structure surface roughness needs to be effectively scaled. The second similitude is the kinematic similitude. This corresponds to the motion similarity. For instance, we may have the turbulent flow in prototype, but the flow in the small scale is laminar. Thus, the kinematic similitude is not satisfied. The third similitude is the dynamic similitude, meaning all the forces acting on the structure and the model are similar, use certain similitude laws. This dynamic similitude can be guaranteed by ensure the same non-dimensional numbers for the full scale and the scale model. For instance, the Reynolds number, which is the ratio of the inertial force over the viscous force, must be same for both model and the prototype. Or for the problems with fluid compressibility, the Mach number m must be same for the model and the prototype. For the problem of fluid compressibility, the dynamic equation for the Newtonian fluids for water and air can be expressed as the Compressible Navier-Stokes equation. The continuity equation is given as in this form. Here, the fluid density is not a constant anymore. The moment equation given as this for 3 velocity components, u, v, and w. Following Stokes, the air compressibility terms are included. And it should be noted here, the fluid gravitational force, the fluid body force has been dropped, since in the airflow, the fluid gravitational force is small and it is not important for the problem. Thus, it can be neglected. This is very different from the problem in the ocean waves, since the gravitational waves take a very important role for the hydrodynamic forces and for the marine structure motions. Now we look at the two geometric similar systems, S1 and S2, with different lengths L1 and L2, see in this picture. But generally, these two geometric similar systems are not identical, since The governing equations for these two structures are same because the Navier-Stokes equation is the governing equation for both structures. However, the boundary conditions are not the same since L1 is larger than L2. However, we may say these two geometrically similar systems can be dynamically similar, that is, S1 is similar to S2, if the following conditions are satisfied. The boundary conditions are similar for both systems according to certain similitude laws. The force and hence the motion are similar according to the certain similitude laws. But the question is how we can guarantee these two systems S1 and S2 are dynamically similar. The first thing is that we need to non-dimensionalize the Navier-Stokes equation. Use the non-dimensional parameters, the coordinates x prime, y prime, and z prime, which are all non-dimensionalized with the characteristic length L. As such, geometrically, we can transform the original system S1 with the length L to a transformed standard system S prime, which has a unit characteristic length 1, C here. And we can also see the parameters in the free stream are all with the subscript 0, the U0, P0, and the rho 0. We can also normalize the velocity using the characteristic velocity U0 as this, and the long-dimensional pressure P prime, and the long-dimensional density rho prime as this, and the long-dimensional time T prime given in this. So based on these transforms, we can say the original system S and its transformed system S prime are similar. That is, S is similar to S prime because the geometric, kinematic, and dynamic parameters are all scaled as seen in these non-dimensional relations. So apply the long-dimensional parameters to the Navier-Stokes equation. We have the continuity equations, the original continuity equation, and the transformed continuity equation. And it can be seen both have same formula. And for the momentum equations, the original momentum equations and the transformed long-dimensional momentum equations are slightly different. So we have the non-dimensional expression in here, named as Reynolds number, defined as this. And we have also the long-dimensional pressure pi p given as this here. So as such, we transform the dynamic system S to the non-dimensional standard system S prime with the governing equation of the transformed standard non-dimensional equations. Now we can examine the non-dimensional pressure. For the air, we can assume the air is an ideal gas. This assumption can be accepted for most engineering applications. And the equation for the ideal gas given as this. Here, P0 is the absolute pressure R is the specific gas constant, and T0 is the absolute temperature in Kelvin. And we can also have the expression for the free stream speed of sound given as this A. Here, gamma and R can be roughly taken as the constants. Therefore, the speed of the sound would be only dependent on the absolute temperature T0. So the non-dimensional pressure is given as this, and finally, in this form, here m is the ratio of the flow velocity over the speed of the sound, the Mach number. So after all these derivations and the analysis of the ideal gas equation, we can have the non-dimensional Navier-Stokes equation, the non-dimensional continuity equation given in this form, and the moment equations given in this. Here we use the Reynolds number Re in the equation, and the Mach number m here in the equation. As such, we have transformed the dynamic system S into the standard system S prime. Now we look at the two geometrical similar systems, S1 and S2, and both have the transformed standard system S1 prime and S2 prime. It should be noted, these two transformed systems, S1 prime and S2 prime, are geometrically identical. So for the system 1, we have its non-dimensional Navier-Stokes equation expressed in this form, and the non-dimensional parameter Reynolds number Re1 and the Mach number m1 are defined as this. Similarly, for the system 2, its non-dimensional Navier-Stokes equation is given in this form, and the corresponding non-dimensional Reynolds number Re2 and the Mach number m2 are given in this form. So after the transformation for these two geometrically similar systems, S1 and S2, we have two geometrically identical systems, S1 prime and S2 prime. But they are not dynamically identical because of the different governing equation. Due to the different Reynolds number Re1 is not equal to Re2, and the different Mach number m1 is not equal to m2. Therefore, these two transformed standard systems are not dynamically identical. For the transformed standard system, S1 prime and S2 prime, they are geometrically identical, and they could be kinematically and dynamically identical when the Reynolds number Re1 equals to Re2 and the Mach number m1 equals to m2. More specifically, in these equations. As such, the transformed system S1 prime and S2 prime would be both geometrically and dynamically identical, since they have same geometry and their governing equations are same. Hence, we can say S1 prime equals S2 prime. So if we have same Reynolds number and the Mach number given by this RE1 equaling to RE2 and M1 equaling to M2, which means both system 1 and system 2 have a same transformed standard system S prime. Since both S1 and S2 are geometrically and dynamically similar to the same transformed system S prime, thus we can say systems S1 and S2 are geometrically and dynamically similar, since the transformed system from S1 to S prime and from S2 to S prime would be equal, given in this. And from this equation, we have the relation given as this. So based on this, we can define the scale factor epsilon as this. This is the scaling factor for the scaled model from S1 to S2. So if we have the similar system, S1 and S2, they are geometrically and dynamically similar. And we'll see what the problem we'll have when the same fluids are used for both prototype and the scale model, since in that case we have the same density rho 10 equaling to rho 20 and mu1 equaling to mu2. The Reynolds similitude requires this equation, and we can cancel out the density and the viscosity. So we have the expression as this, and we obtain the velocity for the scale model is given as this. This means the Reynolds similitude would require a higher airspeed than that in the prototype. So this is the same as we have obtained in the talk on fluid similitude. The Mach number similitude requires the relation as this, and since the same fluids we use, therefore the speed of the sound A1 equaling to A2. Therefore, we have the same free stream speed for the model and for the prototype, regardless what the scale factor used for the scale model. Therefore, for a scaled model, epsilon is larger than 1. In the conventional wind tunnel test, the Reynolds similitude and the Mach number similitude cannot be satisfied at the same time. This is a similar conflict as we have shown in the talk on fluid similitude. So in the second part of the talk on this topic, I will talk how we can solve the conflicts in the small scale test in wind tunnels.